All right. Hey, everybody. So we are coming back from spring break and we are picking up where we left off, which is to say we are jumping into chapter 6, Introduction to Functions. And what I want to do in this video is just highlight some key important definitions about functions, domains, and codomains, as well as images and pre-images. So let's get into it. First of all, a function, right? We'll use this notation here. So we're talking about a function f. We're going to be talking about two sets, the set A and the set B. So when I talk about a function, what I really mean is a function is a method of mapping elements from a given set A, that will be our domain, into another set B, that is our codomain. Right, so A and B are two different sets. Oftentimes they will be sets of real numbers or subsets of real numbers. And F is a rule that defines how you map elements in set A into elements in set B. And the only rule that we have to satisfy is that no element in A can be mapped to multiple elements of B. In other words, every element of A gets mapped to, at most, one element of B. And I should say that in our pre-calculus class or calculus or what have you, in earlier math classes, this has a nice name that you're all probably familiar with. This was our vertical line test. Right, so that was simply, the vertical line test was a way of testing to see that no two y values were getting mapped to by the same x value for our usual notation, y equals f of x. So this means that the structure of a function can be very flexible. It can be used in several situations. In fact, we've already seen it used in the example of sequences, right? So our first example of a function was actually a sequence. Sequences are functions, from the natural numbers, from the natural numbers into the real numbers, right? So that was our a sub 1, a sub 2. We could also think of that as a function like f of 1, f of 2, and so on. And then we have functions that we might be more familiar with, a function from the real numbers to the real numbers, which we might see in a calculus class, something like x squared plus 2x plus 1, or something like the square root of x. I just want to highlight that when we use this notation, right, we know that the square root function, if I were to graph it the way we normally do, right, with an x-axis and a y-axis, the function f of x equals square root of x looks like this. Right? And so its domain and its codomain, maybe I should say the set of points that we can actually plug into the square root function and the set of points we get out of the square root function are actually subsets of the real numbers, right? I'm allowed to plug in any number from 0 on up to infinity, and the outputs will be numbers from 0 up to infinity as well. So even though I sometimes use this notation, f is a function from R to R, and I list R as both our domain and codomain, it is worth saying that sometimes this shorthand will represent functions whose actual true set of points that we can plug in and set of points we get out are subsets of R as opposed to all real numbers. All right, and so that helps to motivate the next two definitions, that of an image and that of a pre-image, right? So we have if a set F is a function from A to B, and we take two sets, C and D, then I can talk about the so-called image of C and the pre-image of D. And I just want to maybe talk through this definition a little bit. So the image of C is defined to be the set of points B in B. So it's a set of points in the codomain for which f of C equals B for some element of C, right? So to say it more plainly, the image of C is the set of all points in the codomain that get mapped to by some element of C. Similarly, the pre-image of D is the set of all points A in the domain for which f of A equals D for some little d in set D. So the pre-image of D, said plainly, is the set of points that map into D. the preimage of D is the set of points that map into D under the function. Okay, and we have two different notations for these. I'm going to move my picture down here for a second. The image of C, we will often use this notation. So it's going to be, instead of just f of x, I'm going to say just f of C, capital C for my set C, right? And so that is taken to be the image of C. And similarly, the preimage of D is often written as f inverse of D. Right, and so worth saying out loud, of course, we're sort of co-opting our usual like f of x notation or f inverse of x, but when I write f of c or f inverse of d, these are each sets. I'm using this notation as a way to describe a set, where f of c specifically is a subset of the codomain, and f inverse of d is a subset of the domain. So let's see an example of this. For the function f of x equals x squared, I can draw the usual picture that we love to draw. So there's our function, f of x equals x squared. And then I can think about different images and preimages of different sets. So let's think through this a little bit. If I were to take the image of the set, let's say the set from 1 to 2, right? So 1 to 2 is a set. That's the closed interval from 1 to 2. And if I were to take f of that, now I'm taking the image of the set 1 to 2. And so I would look from 1 to 2, and I would try to see for all of the points between 1 and 2, what are the image points? So what are the points in the codomain that get mapped to from the points between 1 and 2? So between 1 and 2, I'm really hitting all of these points on the function, and those are coming from the codomain points from up here at 4 down to here at 1, right? And so the image of the set 1 to 2 is really this entire range of numbers in the codomain, and so that is the set 1 to 4. At the same time, I'm going to pause the video here and draw a quick copy of this picture. Okay, so now we have our picture. And if we wanted to talk about a preimage, and this is kind of interesting, if we took the preimage, f inverse of the set, I don't know, just to keep it interesting, let's use 1 to 4. Right, so the preimage of the set 1 to 4, that's going to be a subset of the domain, and it's specifically going to be all of these points, or all of the points in the domain that map into this range here from 1 to 4. And we actually see that there are two different intervals in the domain that map into this range. Right, so over here, right, we see that every point between 1 and 2 maps into the range of 1 to 4. Maybe that's not so surprising. But at the same time, we also see that there's this range over here. Right, from -1 down to -2. Everything in that range will also map into the window of 1 to 4. And so in fact, we see that the pre-image of the set 1 to 4 actually has two different intervals. It will be the interval -2 to -1 union the interval 1 to 2. So that's kind of interesting, right? And so we can talk about finding images and finding pre-images. I'll just point out that if we wanted to actually compose these, so write it down here at the very bottom, if I wanted to calculate the pre-image of the image of 1 to 2, this notation technically makes sense, right? 1 to 2 is a set. f of 1 to 2 is its image. That's a set in the codomain. And so f inverse of that, the pre-image of that, would be a set in the domain. And from what we've just seen, this would be not just 1 to 2 again. We wouldn't just get back 1 to 2, but we would get this extra set as well. So f inverse of f of 1 to 2, which is again notation to represent the pre-image of the image of 1 to 2, will represent, or I should say, will give us a set in the domain that in this instance is actually larger than the original set 1 to 2.